Welcome back to this third lecture in this series on concurrent programming in Java, specifically on concurrency state models and patterns. This week we're going to have a closer look at safety and synchronization. First, we'll have a look at how interaction is modeled in FSP, the final state process modeling framework. Then we'll see how to guarantee safety, we need to worry about synchronization in critical sections of concurrent code. We'll see how locks are used to guarantee atomicity, and we'll have a closer look at the busy wait mutual exclusion protocol, one of the old classic ways of ensuring safety in critical sections, and we'll see it's not so easy to convince ourselves that this algorithm works. We'll see how FSP, and in particular LTSA, the analysis tool which does model checking, will help us in specifying the safety properties that we want to hold true, and we can apply them to our FSP models of concurrent programs, and in particular to the busy wait mutual exclusion protocol to convince ourselves that it actually works correctly. Finally, we'll have a quick look at conditional synchronization, how we can model it with FSP, and how classically with some simple design patterns we can model this in Java. So first of all, let's dive directly into FSP and see how we can model interaction. As we've seen last week, with FSP, we can model finite state processes, each of which can take a sequence of action. So every finite state process essentially models a sequential process, and it can take various actions one after the other. A finite state process can also perform non-deterministic actions by choice. And we can take multiple finite state processes and compose them, and we get a cross product of the possible actions. However, things start getting interesting when these processes can interact with each other. In FSP, that's modeled in a very simple way by having actions which are named identically. So if two processes share any actions, FSP assumes that these actions are performed together as a single synchronous action. So if one process wants to perform an action X and another process also is capable of performing action X, then the first process will wait until the other one is ready to perform that action together. So actions which are not shared, so that they're not so every process has some alphabet of actions that it can perform. If these alphabets overlap, then LTSA assumes that those are the actions that are shared and must be synchronized. Here we have an example of two processes, one which produces things, a maker, and another which consumes things, a user. And the maker can perform two actions, make and ready, and the user performs the actions ready and use. Notice that the only shared actions here are the one called ready. So as a consequence, LTSA, when analyzing the system, if we compose maker and user together, will assume that make and use are independent actions which can be performed without any synchronizations, but the ready action can only be performed when both processes, maker and user, are ready to do them at the same time. Now, recall that the meaning of a finite state process is the set of traces that can be produced. So, for example, with maker, we have the trace make ready, make ready, make ready, and so on infinitely. User has the trace ready, use, ready, use, ready, use. Now, when we compose these two processes together, maker has two possible states, and user has two possible states. Composing them gives us four potential cross products of states, where maker is in one of its two states and user is in one of its two states. There are four possible combinations. But whereas before these actions could be performed independently, Now we have one action which is performed in tandem. So as a consequence, we might get fewer possible actions taking place, fewer transitions between these states than if they were independent, and eventually we might even have fewer total states, as we'll see in some examples. Now, the question here now is, what are the states of the label transition system, and what are the traces that we can achieve? Before we have a look in LTSA, I strongly suggest that you pause the podcast and just try and, on pencil and paper, try and figure out what these two processes look like. They're pretty simple. They just have two states. And what the cross product of the combined processes will be. And then try and figure out for yourself what the possible transition should be. Now, assuming that you've come back, let's have a look at LTSA and what it looks like there. So here we have LTSA, and the specification of the two processes and their composition is already loaded in. We can compile this, we can compose it, and now we see here is the maker. It has two states. Initially it's in the state 0. It can do a make and it can do a ready. Here's the user. It can do a ready and a use. When we compose these things together, we have a new process with potentially 4 states. There might be fewer, there couldn't possibly be more. But let's have a look. Maker initially can perform a make and would then like to do a ready. User would like to do a ready, but it cannot do it until the maker is in its initial state. So this leads us to a composition which looks like this. Initially, the system can only perform a make. At that point, the two processes together want to perform a ready action. That's the only thing that can happen. And at this point, either the maker can make or the user can use. If the user uses, we go back to the initial state, or if the maker makes, then the user can use, and then they together perform a ready action. So we do have the combination of all 4 possible states. However, the possible transitions between them are fewer than would be the case if the ready actions were completely independent of one another. Suppose, for example, if we edit this, and instead of having the synchronized ready actions, we have 2 separate ready actions, ready 1 and ready 2, and now compose them, what do you think would happen? Well, let's save this for the interactive session. I suggest you figure it out yourself on pencil and paper, and then try it with LTSA, and then we'll discuss it when we have the session together. Now, in this particular case, there's a ready action which is synchronous. What we're not modeling is any kind of direction with the common actions. So we would expect that once a maker has made something, it would signal to the user that something is ready, and after the user has used it, it might signal back to the maker that it has used it. So that way the two processes could stay in sync in a nice way. This is known as a handshake. In LTSA and FSP, there is no notion of directionality in actions. It's entirely up to us by convention to model that and to think of certain actions as being a message sent from one process to another. This is purely convention and is not part of FSP itself. So here, for example, we have version 2 of our maker. It makes something, then it signals to the user that it's ready. Then the user uses it, and then the user signals back that it has used it. Of course, these are purely synchronous actions, but we're modeling the case where this handshake is going back and forth. In this particular case, we have different versions of the maker and user with additional states. Notice that maker version 2 here has actually 3 states. There's the initial state, after it's done a make, After it's done a ready and after it's done a use, it goes back to its initial state. So that means that there are 3 states. Also, the user has 3 possible states. Interestingly, this would lead to a total of 9 possible states in the combination, were the interactions totally unsynchronized. This, however, is not the case. I suggest you stop the podcast again for a moment and work out with pencil and paper how many actual states do you think would be in the combined process, and what would the traces be. When you come back, we'll have a look in LTSA what it looks like. So, assuming you're back now, let's go to LTSA and we'll load in the second version of the maker and the user. We can compile and compose these and have a look. Here, as expected, the maker has 3 states, as does the user. Combining these would lead to 9 potential states. However, because these actions are synchronized, particularly the ready and the used actions, we actually only have 4 possible reachable states. So initially, the maker makes something, and then it waits for the user and the maker together perform the ready action. Then there's the use action, and we come back with the end of the handshake that the item made has been used. So we have, with 2 very concurrent processes, actually combined them, and through the use of the handshake ended up with a rather sequential kind of behavior and no non-determinism whatsoever. Fine. Now let's have a look how some of this machinery can be used to help us in synchronizing critical sections, and we'll start seeing what the possible problems can be in terms of guaranteeing safety. Safety problems can be understood, particularly in object-oriented programming, in terms of class invariants being violated. So a class invariant states what the possible consistent states of an object may be. Here we have an object visualized here, represented as a box with a bunch of different methods, and this object is going through a number of different kinds of states. When we start executing a particular method, we assume that the object is in a consistent state. So this consistent state is expressed by class invariant. It expresses what the relationships may be between, what are the possible legal values of instance variables or relationships between them. Every public method can assume that the object is in a consistent state, in particular when the object is initially constructed. While a method is executing, say method M1, it may temporarily be in an inconsistent state, but when the method is concluded, it should then once again be in a consistent state, so that it should be clean. So initially we assume the object is clean, it's in a consistent state. It starts doing some things. Temporarily, it may be out of sync, but then once we've completed our computation, whenever we leave that method, once again, the object is in a clean state. Now, what happens with concurrency? With concurrency, another thread may come in while this thread is executing. So here we have the a thread, say a red thread, which is running here. And this red thread may be in a particular point. And then a green thread comes in, and it assumes that the class invariant holds, but if there is no synchronization, it may end up seeing an intermediate state of the object, which is not clean, because the red thread is in there. So that means that this period here, where the red thread is working with the state of the object, this can be considered to be a critical section. So if the object is in a dirty state and another thread seizes, this can lead to a catastrophe. So everything that we know about design by contract falls apart if objects threads are able to come in and see an object in a dirty state. So what we want to do is we want to protect such resources from these dirty states by formalizing the notion of a critical section and making sure that at no point in time are two threads together in the same critical section. Now, there's a notion in concurrent programming which is that of a race condition. A race condition exists if safety may be violated by bad timing. That's what we saw on the previous slide. If the green thread comes in just at the point in time when the red thread is doing some dirty stuff, then that may lead to a safety violation just because of bad timing. So that's a race condition. So we want to avoid race conditions in our programs. Here, for example, is a badly programmed class. Well, we deliberately programmed it badly. And the idea is the following. We have an account object which supports deposits and withdrawals from an account. And the withdraw method here looks to see what the whether the precondition for the withdraw method is fulfilled. And if it isn't, so if the assets are not available to cover the amount that should be withdrawn, it does a loop and it busy waits. So it does a thread.yield. So just every once in a while, it gets scheduled again. Maybe it should do a sleep there because otherwise it's going to be really looping quite frequently. And then once this condition holds, then we proceed and perform the withdrawal, check our invariant, and we leave. However, suppose at some point in time here, after we've confirmed that the precondition holds, but before we've actually performed our action, suppose another thread may come in. We can simulate this here by performing another thread.yield. So this artificially introduces a race condition in our code, which is of course not a good thing. So by doing this, we will produce the situation that possibly another thread may come in, perform a withdrawal, and then afterwards the precondition that we just checked is no longer true. So here we are in IntelliJ. Here's our bad account class. We have the thread.yield, which will provoke our race condition. We will perform our action and afterwards check our invariant. The invariant was, as before, simply checks that our assets are greater than or equal to 0. We have our test case, which performs a certain number of times, 100 times, deposits and withdrawals, and we expect at the end that the assets will be set to 0. The test case, we actually are expecting an error, but we've set the test case to be a normal one, so we should expect this test to fail. If we run this now, we will indeed see that there's an error occurring with our bad account, and the amount that we're expecting at the end is 3 rather than 0, so something is completely wrong with the computation of the amount of the assets after these withdrawals and deposits. I should point out that it is very hard in concurrent programming to provoke race conditions. So there may be a race condition in your code, and you may have to, if you want to build a test that demonstrates that there is a potential safety violation, you may have to run the test a large number of times before you actually provoke that. And it may be the case that there's an error in your code, but you never actually succeed in provoking the race condition. And as a consequence, it's very hard to write tests that prove or that give you a high level of confidence that your concurrent programs are correct. And this is why we need, on the one hand, design patterns to ensure us that the code will work correctly, and on the other hand, some formal tools that will help us conclude that our algorithms preserve certain safety properties. We'll see shortly how we can specify and check such safety properties. We saw an example that looked like this in the very first lecture. Here we have is pseudocode, a couple of programs. So there are two processes, process A and process B, and they both try and increment a variable called x. Initially, we assert that x equals 0. Then we run in parallel process A and process B. They both read x, add 1 to that value, and then update x with that value. And then in the end, we want to assert that x is 2, most likely. However, there may be other possible values. So the question is, how can these processes interfere? Well, this turns out to be more or less the same as the question, what are the atomic actions here? So let's try and abstract away from the code, or the pseudocode in this case, and model these guys as finite state processes. In this particular case, every action that is performed by a finite state process is an atomic action. And we have to ask ourselves, well, what in our original program should be considered to be atomic? Here we're modeling, on the one hand, we're modeling the notion of a variable as a process. So here's var, and the var can take various, has various states, and the states are expressed as this parameter u. Initially, the variable has the value 0, and u ranges over t, which goes from 0 up to a value n, which is in this case 3. In other words, var is a process with 4 possible states: var 0, var 1, var 2, and var 3. So initially, var is equal to var 0. var at any point in time will support actions read and or write. At any point in time, if the value of var is u, so say var 0, then we can perform in the state var 0, we can read 0. In any state, we can write any other value v. So if we're in state var 0, we can read 0. If we're in state 1, we can read 1. If we're in state 2, we can read 2. And if we're in state 3, we can read 3. But in any one of these states, we can read any possible value of v from 0 to 3. Reading doesn't change the state. So if I'm var 0 and I read 0, I stay in state var 0. If I write a v, then I'll jump to state var v, whatever that is. We can see the visualization of this in the following slide. Here we see the var process. It has 4 possible states, and in any one of these we can perform the read action. But if we perform a write action from any one of these states, we can write 1 and go to state 1. We can write 2 and go to state 2 from any one of these. Here we can see from any one of these states, we can perform action write 2 and go to this state. The other process is the increment process, and it's the one which will read and write. So these are the processes, the two A and B processes that are attempting to read and write this variable. It's a sequential process. It tries to read. It will read any value from 0 to 2, and then it will write the incremented value. So if it reads 0, it will write 1. If it reads 1, it will write 2. And if it reads 2, it will write 3. It cannot read 3 and write 4 because we don't want that to allow. So it'll read, write, and then stop. There's a little thing here which is quite important. We add to the alphabet of this process the things that are missing, which is var alpha. Var alpha says, in principle, inc could perform any of the read or write actions with any possible argument. If we leave that out, then LTSA is going to read this and say, oh, inc will never read 3. We'll just assume that that's an independent action. And that means that the read 3 action could happen at any point in time independently by the variable. But that's completely crazy, because we don't want the variable to independently start performing actions on its own. So that's why we need this. Later on, we'll have a look and see what happens if we leave that out, and it will actually break the analysis. So it's a small point here, but it's important. Now let's look at our incrementer. The incrementer is this process with just 4 states. It can read 0 and write 1, it can read 1 and write 2, or it can read 2 and write 3. So those are the 4 possible states. If we put an incrementer and a variable together concurrently, then we get the following process. So no great big surprises here. Here we have our variables, here we have our inc, and here we have the sequential composition. We compose these guys. Here's the variable. Let's make it a little bit bigger so that we can see all the bits and pieces. So the variable has 4 possible states. Here's our incrementer. And if we compose these guys together, we get a very well-behaved process. Let's go back and have a quick look here. What happens if we leave off the plus var alpha? We've already prepared that on the next line. If we compose this and have a look, it looks pretty similar, but when we compose them, there's weird stuff going on here. Because at any point in time, there are actions that I can perform that I shouldn't be able to. So in particular, the incrementer could never perform a write of 0, because 0 is not bigger than any other value that we could read. So LTSA assumes this is an independent action. And since a write of 0 is always possible, that means that the variable could spontaneously write 0 at any point in time. This is completely crazy, and to avoid this behavior, we simply explicitly say, okay, we know that the incrementer will never do a write of 0, but please pretend that it could. And that's why we say plus var alpha. So it includes in here a read of 3, for example, and a write of 0, even though these actions will never be performed. And this ensures that we get coherent behavior. Now, we saw that inc has 4 possible states and var has 4 possible states. Combining these things leads potentially to 20 possible states. But if we look at the combination, so here I have the combined states, the left-hand side are the states of the variable and the right-hand side are the states of the incrementer. Initially, they're both in state 0, but notice that all of their actions are synchronized. They can't perform any actions independently. So initially, what's possible? The only thing that's possible here is a read of 0 or a write of anything. But the incrementer doesn't want to perform a write of anything. The incrementer just wants to perform a read. So the only action that the two can perform together are a read of 0. The incrementer is prepared to read 1 or read 2, but in this state the variable does not support read 1 or read 2. The variable is prepared to perform any kind of write, but inc is not. So the only thing they can do together is the read of 0. So that means the only thing that's possible initially is this action, read of 0. Then in this state, well, we can read 0. That's the only thing that the variable will support. And the incrementer, the only thing it wants to do is write 1. But the only thing they can do together is write 1, which brings us to this state. So that means the incrementer wants to go here, and the variable wants to go there with the write 1 action. That brings us here. And then essentially we're done. So nothing else is possible. So at this particular state, here, the variable is willing to support various actions, but the incrementer is done. There's nothing that they can perform independently, so we're essentially over. So from all of these 20 states, only 3 states are reachable, and all of the actions are synchronized, so we get a very simple result in the end. And this explains what we see in LTSA. In LTSA, the combined action when we're drawn is this very simple process, which is exactly what we got through our pencil and paper simulation on the slide. Now let's have a look at locking and how locking can help us protect critical sections, which is, I'm sure, no surprise to anyone. But we'll see how we can model it in FSP, and very shortly we'll see how we can reason about safety properties in the presence of such locks. So, with our example, without any synchronization, current threads may interfere. So here, if we go back to LTSA, instead of our sequential process, let's suppose we make a parallel incrementer. So let's get rid of this guy, and now we have a parallel incrementer. We have a variable as before, and we have 2 incrementers. We prefix each of these incrementers to distinguish them. So this is thread A, and this is thread B. They are identical, except all of their actions are prefixed by an A or a B. If we compile this, we'll see them here. So this is incrementer A, the one thread, and this is incrementer B, the second thread. They're identical to what we had before. It's just that all their actions are prefixed, so we can tell them apart. Now we want a variable, but this variable is just like it was before. However, we want it to listen to both threads A and B. So now we prefix all their actions by A or B. If we look at what this looks like, it's identical to what we had before, a little bit more cluttered. So here in the initial state, we're able to read 0 from either A or B, and we're able to write 1, 2, or 3 listening to either thread A or B. So now we've expanded our program. We have, again, a single shared variable and 2 threads A and B that are trying to access it. And this, I argue, is modeling the little bit of pseudocode we had a few slides ago, where we have our 2 threads trying to read a variable and increment it. Now, if we compose them, we get a process that looks like this. Initially, A can read 0, and then A can write 1, then B can read 1, and B can write 2. So we get the final value 2. Or B can read 0 and write 1, and then A can read the updated value 1 and write 2. And so we get to this very nice state number 4. However, what's also possible is that A could read 0, and then B could read 0, and then B writes 1 and A writes 1, and the final value is 1. And we can reach this, as you can see, the state 7, by a number of different paths. So that means in a variety of different ways, we can reach this very bad state here. Now the question is, how can we reason about this? Can LTSA help us detect that there's a safety problem? because there's nothing here in this diagram to distinguish or to tell us that there's something worse about state 7 than there is about state 4. Before we get to that, let's have a quick look at locks. Here's a simple lock process. The lock just performs two actions, acquire and release. Now we can have our incrementer declare that the read and the write forms a critical section. So here's a new incrementer. It first tries to acquire the lock, then it reads the variable, then it writes the variable, and then it releases the lock. Otherwise, it's just as it was before. So here we are in LTSA, and we have the incrementers as before, we have our variable as before, and we have the new lock. Now we compose the variable and the two incrementers together with the lock. If we look at this, here's our variable as before, a little bit cluttered, but more or less readable. Here's our lock, and the lock now has been prefixed, so it will listen to either process A or process B. Our incrementers, which are slightly more complicated than before because they do an acquire and release, but our incrementer will acquire the lock and then read either 0, 1, or 2, increment that value, write it, and release. If we compose these guys together, now we get a process that looks like this. This is much cleaner. So either A initially acquires the lock, reads and writes, releases, B acquires, reads and writes, releases, or B first acquires, reads, writes, releases, and A does, and we finally get to the same unique final state. So this is what we see here. These processes now are synchronizing the critical sections by sharing a lock. In Java, of course, we have locks which are given to us essentially for free because any object can serve as a lock. And we have synchronized blocks which take as an argument the lock to be used to acquire and release. So synchronized block simply says at the beginning of the block, we acquire the lock on this object, and at the end we release it. And synchronized, if you declare a method as being synchronized, that's just syntactic sugar for putting a synchronized block around the whole body of that method. Every object has a lock, and threads can use them to synchronize with each other. Since usually we're interested in objects as monitors, by default, a synchronized method uses the object this, the object that we're interested in, as the lock. But there's nothing to prevent you from using other objects as locks. For example, you may have a complex object that has critical sections that consider various subparts of the object state as separate critical sections and separate resources. In such a case, you could use finer grained locks which focus on the particular subsections of the state of the entire object. This is something we'll look at briefly again in a later lecture. Still, we haven't seen how to reason about safety. We've seen that we have this very nice pattern, this idiom of a lock to protect a critical section, but we haven't seen yet how we can use LTSA to analyze whether safety properties are upheld, and we haven't even come to a conclusion what exactly is a safety property. So we'll come to that shortly, but first, before we do that, let's have a look at an algorithm which is a little bit complicated to reason about and use that as a motivation for introducing safety properties in LTSA. Here's the busy wait mutual exclusion algorithm. We've seen this before, but let's have a closer look at it. So the busy wait mutual exclusion protocol here We've abstracted it a little bit. We have two processes, P1 and P2. P1 and P2 both have critical sections, and we protect the critical sections with a guard. Now, we just saw how we can solve the guarantee safety with the help of a lock, but suppose you don't have locks built in as primitives in your programming language or your execution framework. Well, this was the situation quite some time ago in the 1960s, and before the existence of locks, the question was, well, how do you lock something? So if you only assume that certain simple actions are atomic, particularly writing a value and reading it, then how can you build up the notion of a lock? So here's the answer in this slide. It makes use of three separate variables. There's a variable called turn, which says which process's turn it is, and it's either the turn of P1 or P2. And there are two variables, enter1 and enter2, which express whether a particular process would like to enter its critical section or not. So here's the guard for P1. It initially says, hey, I'd like to enter my critical section. Enter1, I set it to true. However, I'm going to be polite because I don't want to knock you out, so I'll let P2 have its turn first. Now here's the actual guard, the precondition, and it's the busy wait. So while the other process, enter2, would like to enter, and it's P2's turn, I'll skip. P2 does exactly the complementary action. It wants to be polite too. It says, hey, I'd like to enter, but you go first. While it's your turn and you'd like to enter, I'll just wait. So the idea here is one of the two will get in, and it's not too hard to reason that they cannot both be stuck here. It's either P1's turn or P2's turn. It can't be both. So one of these will get out of their busy wait. So it's not possible for it to be stuck there. Then whoever gets into the critical section first, when they get out of it, they'll set their enter variable to be false, and that will invalidate the precondition here for the other one, and the other process will be able to get into its critical section. Looks kind of complicated. Is it correct? There's the question. Well, I would suggest that you stop the podcast for a moment and spend a few minutes thinking about whether, to see if you can prove and convince yourself that this is correct. And when you come back, we'll step through some of the reasoning, which you'll also find in the extra slides in the slide deck. Okay, I assume you've come back now and you spent a little bit of time looking at this. Here's my reasoning. Suppose P1 has entered its critical section. If it did, then this condition must have been false. So let's suppose that enter2 was false. If enter2 was false at this point, that meant that process P2 must have been here. As a consequence, then, when process P2 comes around, it will see that enter1 is true, so it will busy wait there. So that means P2 cannot get in. If I'm in my critical section, P2 cannot possibly be in that critical section. So that looks good. Suppose, on the other hand, enter2 is, so we assume first enter2 was false. Otherwise, P2, turn must not be equal to P2, but equal to P1. If that's the case, then we know that P2 must have set it. The only way this could be equal to P1 is if the other process set it. But we already set enter1 to be true, so that means process P2 is stuck here waiting, because enter1 is true. So that means we get in here, but process P2 must be stuck waiting for us. And the moment we get out and set enter 1 equal to false, then process P2 can be in there. So in both possible cases, it's not possible for both process P1 and P2 to be in the critical section. So are you convinced? Maybe. So the problem with this is it's pretty complicated. There's a lot of state-based reasoning going on here. So this is the motivation for saying, well, let's abstract away from this and see whether with the aid of finite state processes and LTSA, we can do some state exploration and convince ourselves that this algorithm is correct. Let's see how we would do that. And then we will introduce the formal notion of a safety property. As before, we will model variables. We've seen this before. Here's our var process. And we're going to introduce another var process which only takes Boolean values. So it's we could have used a var with the Boolean values with values 1 and 2 or something, but in order to make our FSPs a little bit more readable, we explicitly use the values false and true, and we have actions is to test whether Boolean is true or false, and set to update it rather than read and write. Now we can see our abstraction of the algorithm as follows. Our process P1 is made up of several parts here. We have the initial part of P1, we have the guard, and we have the critical section. And after the critical section, we return and loop. And P2 is identical, or isomorphic if you prefer. Initially, we set enter 1 to true, but we set the turn to be process P2. So far, so good. Then we enter the guard. If enter 2 is false, then we can immediately go to our critical section. If, however, enter 2 is true, then we additionally check if turn is my turn. If so, then we can enter the critical section. Alternatively, if neither of these things is true, then we loop around and we continue to loop with the guard. Once the guard passes, then we perform our critical section. What's the critical section? Well, what's important in a critical section is there must be at least 2 actions, 2 atomic actions. If there's only 1 atomic action, there's no point in protecting a critical section because it's atomic anyway. So in order to simulate this, let's add just a minimum of 2 actions in here to abstract away, to have some kind of abstract actions that P1 performs. And these are the independent actions. So P1 performs A and B, and P2 performs C and D. And what we want to make sure of is that these actions don't end up interleaving. So we really want them to behave atomically. That's the thing we want to check. The rest of this stuff is just the protocol, and these are the shared actions that are part of the locking and unlocking. So in the end, we will build a busy wait process from the various pieces, P1 and P2. We have the enter 1, enter 2, and turn variables. So we have enter 1 and enter 2, they're Boolean, and we have the turn variable, which takes on values 1 and 2. In addition, here's a new piece of syntax in FSP, which is at. It says the only things we're interested in are A, B, C, and D. The rest of the stuff, just factor that away, and let's just call it some anonymous action. We'll call it tau. Okay? That's what that means. Now, let's see what it looks like when we compose this stuff together. Here we are back in LTSA. We have our variables, we have our booleans, we have our process P1 and our process P2, and the whole mess combined together. Now let's compose this mess and see what it looks like. Here's our one of our booleans, pretty simple. We can set it to true, set it to false. We can check that it's false. We can check that it's true. That's all that's going on there. And enter 2 is identical, except it's enter 2. And here's our turn variable, which looks like the variable we had before. We can read 1 or we can read 2, and we can write 2 and get to this state, or write 1 and come back to this state. Here are our processes P1 and P2. They're pretty simple and sequential with our guard, and here's the critical section. So this part of the logic here is the busy wait algorithm. And we want to make sure that these actions don't interleave with these actions. If we compose everything together, well, we get something with lots and lots of states. And notice that everything that we don't care about has been relabeled as tau, and we only see the A, B's, and C's, and D's. But I defy you to read this diagram and make any sense of it whatsoever. Here I can try and compress it a little bit so that we can almost see the whole thing on one screen, but it's a horror. There's even the possibility of minimizing, and what happens here is that LCSA tries to figure out which states are essentially identical, and then we can see a smaller diagram. But it's still pretty confusing, and I think it's difficult for us to reason here about what safety means. So there's our complex diagram. I defy you to make some sense of it. So we need some additional ammunition. Remember that what we wanted to guarantee was that these actions A, B, and C, and D don't interleave. LTSA is an example of a model checker. What it does is we've abstracted away from a program and tried to reason in terms of abstract states. What LTSA does is it does an exhaustive check of all possible states that you can really reach, and it'll tell you which states are reachable. It can also tell you whether certain properties are not violated, in particular safety violations and liveness violations. However, it needs you to tell it what are the safety properties and liveness properties that you would like to have. In particular, we want to make sure that these critical section actions don't interleave. So how can we do that? Here's an example. We could model it as a process. Now, this is just an example. We'll see in a moment that there's a better way of expressing this as a built-in concept in LTSA, in FSP, I should say, of a property, which LTSA will analyze for us. But what's going on underneath can be understood with the help of this additional process. OK is a process that says it's OK for A to be performed and then B to be performed, and we loop around. Or C to be performed and then D performed and loop around. But what would be bad is after an A, if a C would happen, that should lead to an error. Or after a C, immediately an A is performed. That would lead to an error. Well, that's clearly wrong. So if we take that process and compose it with our system, notice all of the actions of this process are going to be synchronized with the system that we have, and that means that all the actions that are there already, the A, B, C's, and D's, will get synchronized with this guy. And if this guy can ever get to an error, that means the original system could get to an error. This guy is our proof that our system is safe if we can see that we never get to error. Here in LTSA, we actually did that. I put that process in there, but I didn't show it to you. Now what we can do is we can compose it together. And now compose everything. There's the OK process. There's the compose thing. We can minimize it. But we still haven't answered the question, can we get to the error state? How do we do that? Well, we don't see where the error state is here. There's a tool inside LTSA which allows you to check various properties. Basically, check for safety says, can we reach the error state? And in fact, it comes back and says, no, there are no deadlocks or errors. Very good. Well, do you believe it? Here's what happens if there is an error. Suppose we break the algorithm. So for example, here, instead of returning to the guard, we essentially ignore the precondition, and the guard now essentially does nothing. It always goes to the critical section. Now if we compose this guy and draw it, we'll again see a big mess. But if we ask it to check for safety, now it says, uh-oh, we have a problem. Suppose we first enter 1, set to true, enter 2, we write 1, enter 1 is set check to true. Here we check true. Both of these guys end up in the critical section, and then an A can be performed and then a C. You can actually check this for yourself. We can go back and change it in other arbitrary ways. For example, if I make this critical section 2 and this guard 2, then we'll also get similar violation. And here, once again, we get a possible interleaving. Now that's an example of what a safety property might look like, but that's not exactly the feature that's supported in FSP and LTSA, and we'll see that in a moment. What we did looks kind of cool, but it has some shortcomings, and that's why we need to be a little bit more thorough about specifying exactly what a safety property is. So a safety property asserts that nothing bad happens. We use the error process to indicate bad behavior. So, for example, if we have this actuator, the actuator can perform a command and respond. What we don't want is after a command, another command would happen. So this would be a violation. So here's the check for the error. However, the error condition state what is not required, what should not happen. In a complex system, it may be very difficult to figure out all the possible paths to the error state. For example, we forgot this possibility. Initially, in the initial state, we also don't want a response to happen. So basically, what LTS offers, instead of explicitly stating which actions lead to the error state, instead a safety property is declared as property, and it looks like a process, but basically what it means is that anything that's not here is considered to be possible and would lead to an error state. Here we are in LTSA. We have our actuator, which performs a command and then an action. And here's the safe actuator property, which says that good behavior is simply command, respond, command, respond, command, respond, and anything else would be an error. We can compose this system, of course, or compile it, I should say, and draw it. So this will show us the system. But what we really want to do is simply check for safety. And it will immediately tell us, yes, command would be an error. If we eliminate this possibility here and run the check again, then it comes back and says no deadlocks or errors. Your system now is fine. Good. So far, so good. So OK, the property that we've defined, should be, however, a deterministic process that specifies which traces are safe. So here is our OK process as it was before, but rewritten as a property. So we don't explicitly have to say anything about which possible paths lead to an error. We say that A arrow B is okay and C arrow D is okay, and we just loop around. Everything else is okay. Anything else would be an error. So this is better than this. For example, with this property, okay, if we initially have an action B or D, that would also be an error. Of course, it's not possible with the program we've constructed, but this is another possible thing which would lead to a declaration of a safety violation. So this is an improvement on writing OK as a process. We write it as a property. We don't have to clutter the description with the description of possible paths to error. LTSA will figure out which are the bad arrows, the bad actions or transitions. So basically they'll say you can do this, you can do that, and any other A, B, C's, or D's which are not the ones allowed here are disallowed. Here's the same program with the busy wait algorithm with OK specified correctly as a property. And now we can simply check for safety, and it says no errors. As before, if we break it somehow, in this particular way and check for safety, it will perform an exhaustive analysis and see if there's any path that would lead to error. If there is, it will tell us. So this is what a model checker is doing. It's checking every possible reachable state, every possible path, and will show us if there is a possible path to an error. If there is none, it will say so. Notice we get to some limitations here in terms of drawing. This one is still fine, but in certain cases, the diagrams that it tries to build end up being so big that it can't draw them. So only with reasonably small-sized models will we actually get something displayed. Now, a safety property should be a deterministic process that asserts that any trace, including actions in the alphabet of that process, is accepted by that process. It's very important that a safety property be transparent. What does this mean? Transparency means that you're taking this special kind of a process and you're composing it with the system, and you're using it to check that no possible path can go to error. But like Heisenberg's uncertainty principle, you don't want to disturb the system. So your checking shouldn't influence the system that you're observing. So all the actions in the alphabet are eligible choices. Composing a property with a set of processes should not affect their correct behavior. That's critical. And as a consequence, we want it to be deterministic. Let's look at a counterexample. Suppose we could write the property P as follows. So here I could have, after an action A, I might take the first path and then do a B and loop, or I might take the second path and go to C and then loop. This is clearly not deterministic. But what does it say? Is A arrow B allowed or not? Suppose the property decides capriciously to do A arrow C, and that means that B would be an error. So here, what does it mean? I could do an A and a C, or I can do an A and a B. So that means from here, A arrow B would not be allowed, but here A arrow B would be allowed. So which is it? So this means that a property which is non-deterministic, a process that is non-deterministic, is useless as a safety property because you can't reason with it. That's why the properties must be deterministic. If you feed this to LTSA, LTSA will spit back and say, that's not a safety property, it's not deterministic. So the compiler, the LTSA compiler, will analyze this and immediately tell you that you cannot use that as a safety property. Here's another little bit of trivia. Suppose you want to specify that some particular action never occurs. You can do it in the following way. So here's the property com. It takes as a base process stop, and it adds to its alphabet disaster. So that process stop does nothing. And however, if disaster happens, then that's an error. So it's a deterministic process, and it will check and make sure that disaster never happens. As the final section in today's lecture, let's have a quick look at conditional synchronization. So a lock is a form of conditional synchronization. It delays the acquire request if the lock is already acquired by some other process. Similarly, if I have a one-slot buffer, it wants to delay a put request if it is full and delays a get request if it's empty. I have one slot. If it's empty, you can do a put but not a get. Or I can do a get once it's full, but I can't do a put until it's been emptied. So we can model this as follows. So here we see this modeled as a finite state process. We have our slot. Initially, a put can be performed. So this is the initial state here, and we can do a put of 0 or a put of 1 or a put of 2. And then a get can be performed, which will empty the slot again and prepare it for a new put operation. Now we can compose such a slot with a producer and a consumer. Here we have a producer that will put 0, 1, and 2 in sequence and then loop around. And a consumer which will get any possible value. If we compose these three together, then we produce a chain, and we can see very clearly that the resulting process is quite sequential and deterministic. Get put 0, get 0, put 1, get 1, put 2, get 2, and loop around. In Java, an object whose methods are all synchronized behaves like a monitor, as we've seen. All the public methods, we don't need to synchronize private or protected methods if they're only reachable from public methods. Within a synchronized method or a block, we can perform a wait or a notify all. This is the monitor behavior that we expect. So this is what we saw last week. Wait will suspend the current thread, releasing the lock, allowing other threads in. It's crucial that at the point when you perform a wait, that the object be in a consistent state. In other words, the class invariant should hold. If you do a wait when the class invariant does not hold, then another thread may come in, see a dirty state, and then you may get a safety violation. That's why in the standard idioms, you will see the waits always at the beginning of a method, only in the guard, before you've made any modifications to the state of the object. Notify will wake up one thread, no guarantee which thread it will be, that's waiting on that object. You should normally avoid notify and instead use notify all. Typically, there are not many threads waiting anyway, but if these threads may be waiting for different conditions, or if you're not sure which one should be woken up, it's always better to do notify all. This simply makes all of these threads runnable. They will eventually run, check their guard condition again, and either proceed or fail and go back to sleep again. Note as well that wait and notify only make sense within a synchronized block. If you're not synchronized, it makes no sense. You may, when you're programming concurrent programs, get a so-called illegal monitor state exception. This simply says that you made a programming error and you put a wait or a notify outside a synchronized block. So watch out for that one. It's a typical mistake made when you're starting programming with Java and concurrency. Here's a slot implemented in Java and it reflects our FSP simulation. We have a put method, which is synchronized, and a get method, which is also synchronized, and they look pretty similar. We're following the standard idiom, notice. We have a synchronized method, we have a guard, and we have a critical section, an action which is performed, followed by a notify all. In the guard, we have a while loop. The body of the loop is a try catch, and within the try we perform a wait. So if the precondition isn't fulfilled, we try and wait. If we're woken up from the wake, we check the condition again, possibly going to sleep. The reason we check again is there may be other methods which are waiting for different things. If we're all woken up, we all should check our conditions again. Here's the get method. It looks pretty similar. Once again, we have a synchronized method. We have a guard, which does a loop for the precondition. If the precondition fails, we do a wait within a try-catch block. If eventually we get out of this, we perform our actions. And if some condition has changed, which might wake up some other thread, then we perform a notify all. In this case, if the slot is now empty, we want to inform a potential putter, which is waiting, a thread which is waiting in the other method. Note again that when we perform the wait, we do so when the object is in a consistent state. We haven't actually performed any actions, so the class invariant should still hold, whatever that class invariant should be. Here's our producer and consumer modeled in UML. Notice that producer and consumer are both active objects. An active object is just a name for an object that has its own thread. Both the producer and consumer have their own actions, and in UML, it's UML convention to have a class box with additional bars at the left and the right to indicate that this is an active object. The producer and consumer share a common slot as which implements the buffer interface. Here's an example of an active object. In our particular case, we have an active object as an abstract class that has a run method, which overrides the run method from its parent thread. And the run method just simply performs an action a certain number of times, whatever the value of count is. And this action is an abstract method because our producer and consumer each will have a different action. So the producer will put and the consumer will get from our slot. And here's the corresponding consumer. So they're both active objects and each has a slightly different action. Here we put everything together. We have a fruit producer and a fruit consumer, and they are going to, as you can guess, produce and consume fruits. So here we are in IntelliJ, and we can see how producers and consumers are put together. We have fruit producers and fruit consumers. So we have 3 producers, Peter, Paula, and Patricia, and 2 consumers. Peter, Paula, and Patricia produce apples, oranges, and bananas. Carla consumes 1 fruit and Chris consumes 2. And we make them run a certain number of times. And when we do that, we can see that we get some arbitrary order of producers and consumers producing and consuming fruits. And if we run it multiple times, we'll see that there's a certain amount of non-determinism in the result, and we get different results each time. Thanks for your attention. This concludes the lecture for today, and we'll be meeting each other shortly in the interactive session, and we'll dive into some more details of what we saw today. Thanks for your attention.